I'm Chris Budd, the Gresham Professor of Geometry. And today I'm going to tell you about energetic mathematics. And just a little bit of history to put this into context. My current place of work is the University of Bath. But before I was at Bath for some years, I worked for the Central Electricity Generating Board, which no longer exists. It's been privatised and changed into many other things. Giving this lecture allows me to tell you a little bit about some of the work I used to do before I went into my current university. So let's talk about great inventions. So every so often they have a sort of kind of contest and people have to write in to identify what was the greatest ever invention. What's humankind's greatest ever invention? The last time they did this, I wrote in and I said, without doubt, the greatest invention of humankind was calculus. Okay, that's what I said, calculus. It's obviously true, but for some reason it didn't win. The winner actually was the printing press, which is perfectly reasonable, but second on the list was fire. And the reason, of course, fire is such an important invention, or stroke discovery, is that all of us as human beings need energy to live. So originally, before anything was invented, as it were, we all took our energy from the sun, and that's, of course, what animals do. But in order to live in colder places like Britain, you need other sources of energy, and the discovery or invention of fire was enormously important in the development of humankind and the growth of civilization as we know it. As human civilization evolved, so other sources of energy became important. So water and wind and other kind of naturally occurring sources of energy were exploited a great deal. So you can turn a water wheel with water and then you can use that to grind corn, and you can do the same with wind, of course. And then in the Industrial Revolution, starting in the 18th century and then onwards, we see the huge change in the way that people live because of the invention of steam, and that gave you both engines which could do mining and pump water and stuff, but also things which could then take you around, give you transport and stuff like that. So energy is hugely, hugely important to every single one of us and will continue to be important as the world's population grows greater and greater. But now, where does most of our energy come from? Well, what is powering this talk, what is powering the lights, what is powering most of what we do is electricity. And the greater majority of the world's energy comes from electricity. Why is that? Well, one of the main reasons is that you can transport electricity around very, very easily with almost minimal loss of power as you do it. You can transport it in a kind of clean way, and you can use electricity to do many, many things when you get it. So high voltage electricity is powering most of the world. And in even areas of the world which don't have direct access to high voltage, still have access to electricity through things like solar power and stuff like that. So my talk today is primarily going to be about electricity. So I'm going to tell you how electricity is used, a little bit, and this is where the maths comes in, of the way electricity is supplied to us and the mathematics of the power grid. And then we're going to kind of look into the future a little bit to see how our energy requirements are going to change in the future and how we're going to use mathematics to help us deal with the way things are changing. So a little bit of history. Here are three of my heroes. So Faraday, again, just a little extra bit of propaganda for me, as well as being Gresham Professor, I'm also Professor of Mathematics at the Royal Institution. And Michael Faraday at the Royal Institution is arguably the person that sort of discovered or invented the modern way of using electricity. In particular, he found by experiment the link between electricity and magnetism, and invented the generator, which allows you to kind of produce electricity as much as you want by converting mechanical motion into electrical power. So Faraday, hugely important guy, came from very humble origins. He was essentially a bookbinder and ended up being arguably one of the world's greatest ever experimental scientists. Following Faraday's basic invention, there was then kind of sort of almost a war, technological war, between various systems to take Faraday's small-scale experiments and turn them into large-scale production of electrical power. And the two kind of main protagonists or inventors of this were Edison and Thomas Edison and Nicholas Tesla, who both developed different schemes for generating large amounts of electricity and transmitting it around. Edison was pioneering what's called direct current, so that's electricity which stays at a constant voltage and constant current. And Tesla pioneered alternating current, where the current goes up and down, and we'll have a look at that in this talk. And the advantage of Tesla's system was that you could change the voltage very easily. That meant you could go into very high voltage. High voltage you can transmit with much smaller loss of energy. And so Tesla's system won out, although Edison tried to discredit Tesla by saying it was more dangerous, which was rubbish. And we essentially owe the modern world and the modern way of transmitting electricity and the fact that we have electricity in our houses and on our factories and in every aspect of our life to the wonderful work of Nicholas Tesla, who was a really colourful character, and I thoroughly recommend you learn a bit more about him if you want. If you think engineers are boring, they're not. Have a look at his life. So these are the pioneers, and it meant that from really the beginnings of the 20th century onwards, electricity has become the dominant source of power that is supplied to our houses, supplied to our factories, and is used to do virtually all the things that we need to live as a civilization. So electricity, the use of it is growing faster and faster. This is results of this was a government report that was produced in 2009. And in 2009, the amount of electricity, the peak demand in the UK was 58 gigawatts. That's 58 billion watts. The total demand over the year, the fundamental unit of power, of energy that you'll get on your electricity bills is what's called the kilowatt hour, which is 1 kilowatt of electricity supplied over an hour. An average household uses between 500 watts and 1 kilowatt. So the total demand in 1 year in the UK was 314 terawatt hours. Currently, the peak demand in the UK is 80 gigawatts. So from 2009 to 2017, we've already increased the amount of electricity we use. This is partly because the population's increased, partly because the economy has increased a bit, and also there is more and more of a shift towards using electricity for things like electrical vehicles and stuff like that. In 2030, up to 96 is predicted, and in 2050, they're expecting the demand for electricity to almost double from what it currently is. So this is a huge increase in the demand for electricity, and that's just in the UK. But supplying electricity isn't quite as simple as you might think. There are various problems with supplying electricity, which means keeping the whole system in balance is quite difficult. One is that once you generate electricity, you basically need to use it. It's not something you kind of can put to one side and use later. It is quite hard to store electricity in large amounts. Gas, when you produce gas, you can put it into a gas container, and when you need it, you can use it. If you produce food, you can store that and use it when you need it. But at the moment, one of the difficulties with electricity production is that the only way we know to store electricity in large amounts is to pump water uphill and then let it go downhill afterwards, and that's actually quite inefficient. And that makes things a bit hard about keeping everything balanced. And the other thing is that if the lights go off, people notice very, very quickly. Okay? It was bad enough in the 1970s when the lights went off and the TV went off, and that was pretty bad. But now, with our huge reliance on the internet and computers, you know, as soon as the lights go off, it's pretty bad. So you're not allowed to do this. Okay, so how is this done in the UK? Well, as I say, when I worked for the Electricity Generating Board in around about the year 1990, the Electricity Generating Board was privatised and split into a number of companies. And some of the companies produce electricity, companies like National Power or EDF. Other companies supply low voltage electricity to your house. So that will be the kind of local electricity boards. But between the producers and your house, we have the thing called the national grid. And the national grid is the company that maintains the high voltage electricity lines between the power stations in your house and kind of controls all of that so that you get in your house electricity that you need at a sort of reliable and constant level. So that's the National Grid Company. So their aim is to provide reliable alternating electrical power from the suppliers, the power stations, to the consumers, and that is you. And their job is to ensure that your voltage in your house is constant at about 240 volts. If it changes a lot, then your electrical devices might either not work or blow up. And also to ensure that it has a near constant frequency. So the frequency of the supply is 50 hertz, and it's important that stays constant, again, for your electrical things to work. And the difficulty is that they need to do this regardless of the power demanded from the grid. So in the middle of winter, when everyone has got all their heating on and during the day, when the factories are working hard or you're cooking and stuff like that, there'll be a very high demand. In the middle of summer at night, there'll be a much lower demand. So the demand from the grid changes a great deal during the day and during the seasons, and the national grid has to provide a constant voltage regardless of that. And that's a big technological challenge, and it's a challenge which mathematics is actually extremely important in helping deliver. And that's what I want to tell you a little bit more in this talk. So it's not easy. And here's a good example. You may remember this guy. If you don't remember this guy, that's Paul Gascoigne. Now, back in 1990, something incredibly remarkable happened. Something which may never, ever happen again. And what happened was that the England football team got into the semi-final of the World Cup. Okay. Incredible. It may never happen again. So the England football team got into the semi-final in 1990. and they were playing West Germany. That was before Germany was reunited, so they were playing West Germany in the semi-final of the World Cup. And it was a really very, very good match. And at the end of extra time, it was a draw, okay, which again was remarkable because England hadn't been destroyed by the Germans at that stage. And Paul Gascoigne had been booked during the course of the match and started crying because he knew he wouldn't get to the final. Okay, so that was this thing. Because it had gone to a draw, the match then went to penalties, which of course we lost. Okay, we're not very good at penalties, but the thing about the penalties was that the electricity suppliers knew that lots of people would be watching the match and therefore had kind of accounted for that, but hadn't counted on it going to penalties. So they were starting to shut the power stations down just at the time everyone was switching on, watching the penalties. And there was a huge swing in the demand on the grid, a swing of 2.8 gigawatts, which at the time was 11% of total capacity, as estimated 1 million people switched on their kettles to make a cup of tea. And that very nearly wiped out the power grid. We got through, but more or less by the skin of our teeth. So these sort of swings can happen, and that was actually the second largest swing in the power grid in recent years, the largest being actually 9/11. Here are some other swings that have occurred. So there we have England versus West Germany and various other things like that. You can see these big ones. This is interesting. So you've got these matches, England-Argentina, England versus Brazil. But here's EastEnders. So that was I think someone got killed or something in those. So these are significant swings. The days of big swings are less now because these were the days before you could kind of watch things on iPlayer or on the internet or stuff like that. So things are moderated a bit more. But these are big swings on the power supply and stuff that you have to take into account if you want to supply regular amounts of electricity. Now, I'm going to a little bit of propaganda here, having worked in the industry. We have essentially avoided large-scale power cuts in the UK. You get the occasional local power cut, but a large-scale blackout of the UK has not occurred, at least in recent times. And that's a tribute to the engineers at the National Grid. This cannot be said of other countries. And this is what can go wrong. In August, 14th of August 2003, there was a storm in the northeast US. And during the course of this storm, some trees were blown onto a power cable and shorted out the power cable. And what generally happens when that happens is that the local area close to the power cable shuts down to avoid severe injury. And then the electricity is routed around other power cables so that the whole network can carry on. The problem with that happening is that those power cables that the electricity is routed around then are taking more current, so more strains put on them, and occasionally they can then short out themselves, and then you get what's called a cascade of one failure leading to another, leading to another. Now, the control systems are designed to avoid that happening so that a wide-scale blackout doesn't occur. But unfortunately, there was a bug in the software. They were, well, you know all about this, they were updating their software. Okay? If anyone's got a microcomputer, you'll know that when you get an update, your computer doesn't work for a week. And essentially that was happening, and the combination of the updating software and the bug and this local failure meant that there was a cascade where the whole network eventually collapsed, And this is the US. There's Canada up here. There's a black thing here. Those are the Great Lakes, which are black. As you might imagine, there's no houses there. But that area there is what's called the Northeast Coast Blackout. That whole area got blacked out. Many millions of people had no electricity for several days as a result of that whole area there. I think some areas were out for about a week. And it wasn't just the US that went down, large chunks of Canada as well. So that was a huge economic disaster, all caused by a failure in the mechanisms to control the grid in that part of America. It's estimated that $5 billion were lost as a direct result of the blackout, and it's a little bit hard to say how many lives were lost, but certainly tens of lives were lost. If a hospital loses its electricity, that's very, very serious, and lives can be lost as a result. So that hasn't happened since in the US. There have been other places which have had big blackouts, most notably Italy a few years ago. And keeping the lights on is very much a huge issue for the engineers of the grid, for you and I as members of the public, and of course politicians lose a lot of face if the lights go out. And repeatedly you get warnings that the more and more demands are being made on the British energy network, and therefore we need to do something about it, particularly building more power stations. So mathematics really is a hugely important tool in helping us keep the lights on. So what I want to do now is tell you a little bit about how the electricity supply network actually works, and then show you how mathematics can sort of predict why things like the Northeast Coast Blackout can occur, and how we can then try to avoid these things happening elsewhere. So let's show you how electricity is basically provided for you. So electricity is produced in the whole in large power stations. I'll talk a little bit more about how it's produced in a second. The large power station then produces electricity at a very high voltage, and the highest voltage, the EHV, which is extra high voltage network, goes at about 400 kilovolts. The reason electricity is supplied at very high voltage is that the higher the voltage, the lower the current that you need to supply a certain amount of power, and electrical power loss is proportional to the current squared. So the lower the current, the lower the loss. So if you have very high voltage, it means there's much lower power loss. So the large pylons that we see marching over our countryside are operating at this 400 kilovolt voltage, or possibly 100 kilovolts. When the electricity gets nearer a town, the voltage is reduced in a transformer, and alternating current you can change the voltage again with almost zero energy loss with a transformer. These are incredible pieces of machinery, which it's then dropped down to what's called the high voltage network, which is 11 kilovolts, and that kind of comes into the towns. And then close to your homes, there will be substations. You can probably see these as you walk around. There'll be an area where there's some machine in there, and outside there will be a lovely notice like "Beware of death," or "To touch these wires means instant death," or "Anyone disobeying this notice will be prosecuted," or something like that. That drops it down to about 400 volts, and eventually into your houses, maybe another drop down to 240 volts for your supply. So that's how the electricity works, produced at very high voltage and then goes around this network at these various different voltages. So let's pick this apart. We'll start with looking at the suppliers. Sorry, that's the grid for the extra high voltage. So we have the UK, the English grid, and then the Scottish grid. And there's actually cables down there which link us up to the French grid as well. And that's what it might look. I did some work in Eindhoven with electricity coming in. This is at 10 kilovolts, and then going around various houses. But we'll get back onto this in a minute. So in terms of supply, one of the big challenges that the electricity industry is facing at the moment is that the nature of the way electricity is supplied into the grid is changing very, very rapidly. This is a graph showing the history up till about 2010, and the top is coal. So in the 1960s, by far, the greatest supplier of electricity was coal-fired power stations, and coal has been going down and down and down. That dip there, by the way, was the miners' strike in 1984, down and down and down. Oil, similarly, has been going down. It went up again during the miners' strike and then down again. Gas is well, there was a thing called the dash to gas in about 1990, where you saw a big changeover from coal to gas as the primary source. So currently, gas is the main supplier of electricity to the UK. That was North Sea gas for a long time, and now we rely more on gas from other sources. We've got nuclear, which reached a sort of peak in the 1990s, has been going down a bit since as nuclear power stations have been decommissioned, but is hovering around about 20%. And this is one I'll come back to quite a bit. This is the renewables, which from an almost zero base are being gradually going up and up and up. This was 2010. We're going to see that shift up even more in a couple of transparencies. So everything is changing. This was the state of play in 2010, with nuclear at 16%, gas at 47%, coal at 29%, and the renewables at 6%. But something very remarkable happened on Friday. I don't know if any of you are noticing or keeping your eyes open, but for me, a very, very significant thing happened this Friday. And what happened this Friday was on the 21st of April 2017 was the first time since electricity being generated in the UK when no coal was used. Okay, so that was the first coal-free day in Britain. We went for a whole day without generating electricity by coal. So that's going from 80% in 1960 down to 0% on Friday. Today, we've probably got coal-fired electricity being generated, but that particular Friday. So that was actually, don't say Gresham lectures aren't bang up to date. Okay. So that was Friday. Fossil fuels, that's coal, oil, gas, and in Ireland, peat, are still the dominant suppliers of electricity in the UK, and a typical power station will produce somewhere between 1 and 2 gigawatts of power. So just to remind you, the current peak demand for the UK is 160 gigawatts. That kind of gives you the order of that. So fossil fuels are producing that. And of course, fossil fuels are not great because every time you burn a fossil fuel, you're producing carbon dioxide, and carbon dioxide is a major contributor to global warming. And if you don't believe me, come to my Gresham lecture in the next series. That's a series which starts in autumn of this year. The idea at the moment is to reduce our dependence on fossil fuels. Nuclear power is currently around about 16%. There are 15 currently active reactors in the UK. They're planning to build another one quite near where I live in Hinkley Point, which is on the North Somerset coast. This particular power station is Sizewell B, and when I was working at the Electricity Generating Board, we were doing quite a lot of the calculations for Sizewell B, and it was built around about 1990 and has operated pretty reliably ever since. And a nuclear power station, again, produces between about 1 and 2 gigawatts of power. One of the big question marks about energy in the future is whether we will have electricity generated by fusion power. So this is a fusion reactor. This is the jet reactor near Oxford. I put question marks for how much generating power that will have. At the moment, they're not generating any power at all. And the story about fusion power is that it's always going to be 30 years into the future, regardless of the date. But that might be a source of electricity generation in the future, although I'm not sure. There's lots and lots of technical things to overcome. Renewables. Renewables are, again, in 2010, 6%. Now, astonishingly, we're up to 25% of the current electricity in the UK is generated by renewables, which, as far as I'm concerned, you may not agree with me, is fantastic. It's a huge increase in the amount that is produced without producing carbon dioxide and without polluting the environment. Hydroelectric is a renewable energy source that's been around, well, for a very, very long time. As I said, water power was used before steam power. And if you go to certain parts of the world, such as British Columbia and Canada, where I go quite a lot, nearly all the electricity in British Columbia is produced by hydroelectric power. There is a hydroelectric system in China called the Three Gorges Dam, which produces the astonishing amount of 20 gigawatts of power. That's 1/4 of the UK's total energy needs. Of course, in China, they have the space to build these things. We couldn't possibly do that in the UK. So that's hydroelectric. Much of Scotland's electricity is hydroelectric. Wind power is the real up-and-coming source of renewable, and I'll talk more about this at the end of this talk. Currently, about 20% of our power is generated by wind. A typical wind power station is about 500 megawatts, which is rather less than a coal-fired or nuclear. But in 2016, more electricity was generated from wind power than from coal. That was when that crossover point was made. And of course, on Friday, there was no electricity generated by coal at all. So these are kind of large renewable sources. There are also smaller ones, so solar power is interesting. The reason solar power is interesting is that we're seeing a shift from electricity being generated in large amounts by power stations at high voltage to electricity being generated by ordinary people in their houses. So here is a solar power on a house with lots of panels. You'll be lucky if you get 10 kilowatts out of that. May only get 1 kilowatt or something, but the big shift is that you're seeing lots and lots of small amounts of power generated by solar, and that's all feeding into the grid, and that makes life complicated if you're trying to control the grid. And then a technology which may or may not work is wave power, where in Korea they've got a wave and tidal power. In Korea they have a 200 megawatt supplier. So these are the renewables. Where does electricity go? Well, it goes to us, which might be a factory or your house. And a typical house takes about 500 watts of power, or between 500 and a kilowatt. And what's interesting and what's causing all the kind of headaches for people trying to supply electricity is going to be the increase of the use of electrical vehicles. Now, they're great things, electrical vehicles. They are essentially pollution-free and have many other advantages. But what's interesting about them is to charge an electrical vehicle takes between 1 and 2 kilowatts of electrical power, which is rather more than the typical household is going to use. And so that's going to put quite significant extra demands on the grid. Currently the UK household takes about 4,600 kilowatt hours per year. Interestingly, Canada is the largest of all. I assume that's something to do with the cold winters. Okay, so that's kind of set the scene. I want to tell you now a bit about the maths behind the power network. And this is going to be slightly scary maths, so I hope you'll bear with me on this. So in an electrical network, thanks to the invention of Tesla, power is supplied as three-phase alternating current. So what alternating current means is that with time, the current basically goes up and down as a sine wave. So this is very regular, very periodic, and the frequency of that is 50 hertz. So you go through 50 cycles every second. And the advantage of alternating current is it's much easier to raise the voltage and decrease the voltage. And the best way to describe a sine wave is to use a bit of complex maths in the sense of the maths of complex numbers. And you say the voltage at a time t is V, which is a complex number, times e to the I omega t. So if you don't follow what I mean there, just kind of relax a bit. It's just a nice, easy way of explaining what that shape is in terms of complex numbers. And the current is described similarly. So the omega here corresponds to a frequency of 50 hertz, and V and I are complex numbers which allow you to express both the amplitude and the phase of the alternating current. One of the questions I was asked when I was interviewed at Cambridge was, what's the use of complex numbers? And I had enough nous to say, I think there's something to do with electricity, and I was correct. So maybe that's why I got in, I don't know. But this is an important use of complex numbers. So this is how engineers describe alternating current. And what you do to describe the network is you represent the alternating voltage by this complex voltage V and the current I. And here again, here's a slightly scary bit of maths. The power, and that's what we're interested in, that's what powers our machines, our kettles, our lights, and so on, can be calculated by taking the voltage V and multiplying it by the complex conjugate of the current. And that gives you a complex number, P plus IQ. P is what's called the real power. That's the power which is actually used to heat things. And Q is called the reactive power. That's the power which kind of goes in and out of the system throughout the course of the cycle. And the way engineers design a network is that they make estimates as to how much power a typical consumer, that might be a household or a factory or a car which you're charging up, how much power is needed. And they kind of know both P and Q for different households. And what they do is they try to arrange the way power is calculated and generated so that the demands of the household are met in terms of these numbers. So I'm sorry if this is slightly scary maths if you're not used to complex numbers, but the key thing is that these numbers P and Q are things that the engineers either know or can predict. So here's a typical network that you might have where power comes in, and you have these things here which we call nodes, and these nodes are connected up by connectors which are called buses, and you've got various things going on. So that's a sort of typical network. And the way this network is represented when you're doing the grid is you have these nodes. So a node, what's a node? Well, your house is a node. Okay? At each point in the grid, there are points where you have a certain amount of power, or that could be a junction in the network, or it could be a power station. And at each node, you have a voltage, and the letters J and K are referred to which node you're at. You have an amount of power, which is this here, P plus IQ, and a current IJK, which flows between the nodes. So every current network has this kind of description of nodes with voltages, current flowing between the nodes, generating power here. Now, when we design the network, we know what these powers are. We know that your house needs about 500 watts of power. What we don't know are what the voltages are, and what we want to try to do is to make sure that the voltage is as stable as it can be, and that requires solving equations. So let's show you what the equations look like. Again, they'll look a bit scary, so bear with me. Ohm's law says that the current flowing between two voltages, Vk and Vj, is proportional to the difference in the voltage times a thing called the conductivity, which is similar. Again, this is known. This is an electrical property of the wires. And then the power is the voltage times the complex conjugate of the current, which is this thing here. Okay. Again, that looks a bit scary, but the important thing is that the power is proportional to the voltage times another voltage, in other words, the voltage squared. So if you combine all this system of equations, if n is the number of nodes, if S is the power that you demand from the network, which is what the consumers are interested in, if V is the voltage, which is what you're trying to supply, and if sigma is the conductivity of the wires, if you put all this together, you get this horrible looking equation here, which probably has a symbol there you've never met in your life, which is called a tensor product, but that's what we have to work with. But the key thing is that this is what's called a quadratic equation. Now, when you're at school, you learn about these things called quadratic equations. And in around about the year I'm trying to think when it was, about the year 2000 actually, there was a debate in the House of Commons because there'd been a motion that quadratic equations were horrible things which shouldn't be taught to children. Okay. And one of the arguments behind this was that they were totally useless, and why should we bother to teach something which is useless? The moral of all this mathematics, which you can now forget because that's the hardest maths you're going to have, is that, by the way, there's a very, very scary quadratic equation. Electricity supply is all about solving quadratic equations. So if we can't solve quadratic equations, all the lights will go off. If anyone wants to know, this picture was taken from my article, 101 Uses of a Quadratic Equation, which I wrote in response to this debate in the House. So there's a scary quadratic equation about to affect you. So let's talk a bit about quadratic equations, and then I'll show you why they're important in power cuts. Here is a quadratic equation, which is a lot simpler than the one for the grid, but still has all the kind of properties and structure that we need to understand how the grid works. So the simplest quadratic equation, you're trying to find x, and it satisfies the equation ax squared plus bx plus c is 0. And one thing you learn, this equation, by the way, was known by the Babylonians. The Babylonians knew all about this, and they knew how to solve it. And there's a formula for solving this, and the formula in its current form we think was first understood by the Indians, although there was also the Arabic mathematicians came up with it about the same time. And the solution of this equation x is given by this formula here, minus b plus or minus the square root of b squared minus 4ac over 2a. And this equation has two solutions if b squared is bigger than 4ac, and no solutions if b squared is less than 4ac, and that's kind of important. And we'll see why it's important in a second. So there's your quadratic equation, and there is the solution. For the national grid, we don't have one quadratic equation. We have approximately 30 million quadratic equations, corresponding to every single household in the country. But the basic principles are the same. You still have things like this which you need to solve. Here's a particularly straightforward example of a quadratic equation. X squared minus 2x plus c is 0. And the solutions to this are x is 1 plus or minus the square root of 1 minus c if c is less than 1, and there's no solution if c is greater than 1. And I want you to have a look at the picture that corresponds to. Here is c going along here. There's x going along here. And there are two solutions if c is less than 1, and no solution if c is bigger than 1. Okay, so what, you might say? It's a quadratic equation. We know from the debate in the House of Commons that we shouldn't teach these to children because they're useless. But no, I want you to have a think about, look at this picture. Again, two solutions if c is less than 1, no solution if c is greater than 1. In electricity supply, what plays the role of this c is the amount of power we demand from our network. And if you look at the voltage for the network as a function of the power you demand from it, that's what it looks like. Here is, I've drawn three here, curves, each of which relates to how many power stations you got switched on. So this is where you got not enough power stations, that's where you got too many, that's when you got about right. That's the amount of power you suck out of the system. That's the voltage on the system, normalized, and you see you get a curve looking exactly like the solution of the quadratic equation. And what's going on is this. Let's have a look at this one where it's about right. If the power is in this region here, the voltage is more or less constant, which is what we want it to be. If we increase the power sucked out of the system, the voltage starts to drop. And if you go too far on, there are no solutions. And what in quadratic equation land, having no solutions means you've got no solutions. In our world, having no solutions means all the lights have gone off. Okay. So if you draw too much power out of the system, there's no voltage which will work, and literally you get a power cut and all the lights go off. And engineers call this a nose curve. Okay, you can see it looks like a nose. And if you get anywhere near here, that's when you're likely to have a power cut. So you have to be very, very careful to operate over here. And if you go too far on, you have what this phenomenon called a voltage collapse, and the voltage just drops to 0. And if you don't believe me, this is important. If you remember, we had a look at this Northeast Coast Blackout. This is what happened in the Northeast Coast Blackout. Basically, the demand got too much for the power network to deal with its reduced capacity, with the wires having been taken out. And this is time going here. This is the voltage. That's where they wanted to be. And suddenly it dropped to 0. That was in Staten Island in New York State. So exactly what was the quadratic equation predicted actually happened. So here's again our quadratic equation, lurking on the engineer who's trying to work out what to do. And what the engineers do for the grid is they try to design, both simulate and control the network to avoid this voltage collapse scenario. And what that involves doing is writing computer programs which can basically solve large numbers of quadratic equations very quickly to react to changes in supply and demand. And when Paul Gascoigne was crying and so on, they were furiously trying to solve these quadratic equations to make sure there were enough electricity power stations activated to prevent the blackout occurring. Unfortunately, got it right. So quadratic equations are very, very important. So that's where we are at the moment. Let's see where we're heading. So there are a lot of challenges to the future evolution of the power network. One is the shift from coal-fired and nuclear power stations over to renewables, this huge shift. The other is a shift from cars which burn fossil fuels over to electrical supply, which is going to put a significant extra demand on the grid, particularly at night, because most people will drive home and charge their cars up overnight, and that's something we've not been used to, a high demand at night. Equivalently, many households are now putting batteries into their house so they can store electricity overnight as well. And the other thing is the old-fashioned thing that we have power stations that are wearing out, and we need to get new power stations, therefore design them. So a lot of future challenges. And here's a very interesting graph. This is taken from the same government report that I told you about last time. This is the 2009 up to 2050. And in terms of gigawatts, in 2009, 1.9 gigawatts of electricity were produced by wind and marine energy. Virtually nothing by solar, and coal and gas were producing these huge amounts here. Here's the projection for 2050, 93 gigawatts. In other words, in 2050, this report was predicting that virtually the major producer of electricity in the UK will be wind power. With solar second, nuclear third, and CS is carbon capture and storage coal. So that's coal where you're basically capturing the CO2 rather than releasing it into the atmosphere, gas and coal down to almost nothing. So a huge projected change in electricity. So is the answer blowing in the wind? Personally, I'm biased because it's an area I work in, but I think it is. This is a power station I know very well. This is the Thanet offshore wind power station, which is a large amount of turbines around the east coast of Kent. As I said earlier, 20% of the electricity in the UK is currently produced by wind. That's going to go up. In terms of offshore wind power, the UK is the world leader, okay, of offshore. We're certainly in Europe best placed for wind power. There's no other country in Europe a better place for exploiting wind power than the UK. And 14.6 gigawatts of our current electricity is supplied by wind. If I go back to 2009, it was 1.9 gigawatts in 2009. So in just 8 years, we've gone up to 14.6 gigawatts. That's a huge increase. But one of the constant objections people have said about wind is that wind speed varies, and so you can't rely on it in the same ways with coal. You know, you know how much coal there is, and unless there's a strike or something, you know how much they can supply. And this is, you know, a plot of wind over a couple of years, showing how much it varies. But one of the advantages of wind is with solar power, you tend to get lots of energy when the sun is shining, which is when you don't need the energy, and you don't get any energy when the sun isn't shining and you do need it. Whereas with wind power, if there's a storm and you need the energy, you tend to get lots of wind. So it tends to be slightly better correlated. So that's that. But actually, it's not as bad as it looks, because with wind power, you don't really need to predict too far in the future. What companies are most interested in is, have you got enough capacity to supply what we need for the next hour? With a wind station, you've got lots and lots of data of wind speed, and you can use this data. And if you combine this with machine learning algorithms, if any of you were brave enough to go to my big data talk, you will have heard me talk about this. We're actually quite good now at predicting wind speeds up to about 4 hours in advance. And that's really very helpful in making some sort of sense of all the variability of wind. Here's a graph showing how wind power relates to wind speed, and there's a very kind of close relationship. And so a lot of effort's being put into this business of trying to at least be aware of what wind is going to be doing, and that's helping a lot in terms of being able to ensure wind is more reliable as a way of providing electricity for us. And as we move into the future, so climate change and change in wind patterns, again, is going to change the way that wind power is used, but I'll be covering that in future lectures. So again, come along in the fall if again, you're brave enough to hear me talk about climate change. So that's about it. So I just want to kind of conclude. Energy matters to us all. As I say, the kind of big change in human civilization occurred with the ability of us to use energy around us in terms of fire and so on. And the business of applying energy to humanity is one of the greatest challenges we face. It's what one of the governments calls one of its grand challenges in its current way of thinking. Electricity supply networks are already pretty sophisticated and are getting more and more sophisticated as the way we use electricity and the way we generate electricity is changing. In fact, we don't have enough mathematics at the moment to be able to solve all this. There's a lot of research going on at the moment into developing better tools to understand the mathematics to be able to solve all these equations. But the key thing I want you to take away from this lecture is this. To keep the lights on, we need to be able to solve lots and lots of quadratic equations. Thank you very much.